Hello, everyone. Thank you for joining EE Power Day, brought to you by EE Tech Media and EEPower.com, and sponsored by Mouser Electronics. I'm Barbara Vergettis London, Editor-in-Chief of EE Power, and I'll be your moderator for our next session. Before we begin, I'd like to announce our giveaway winners from the previous ZenD keynote session. Congratulations, Stuart Eichen and Werner Strike. You will both receive an event t-shirt and wireless charger courtesy of Mouser Electronics. We'll be in touch next week to ensure we have the information we need to send you your prizes. But now, on to our live session. Evolution of Power System Architecture, brought to you by Advanced Energy. Our presenter is Joe Voiles. Joe is Advanced Energy's Vice President of Marketing, Industrial Power Conversion within Industrial Power Products, and has more than 33 years experience in sales, product marketing, design engineering, and business development. He joined Advanced Energy through the Emerson Artisan acquisition, where he led a sales and marketing team focused on embedded power conversion. He holds a Bachelor of Science degree in electrical engineering from Southern Illinois University Carbondale and a master's in business administration from Lindenwood University. Following the presentation will be a live Q&A. You can submit questions anytime during the session using the chat box on the right. We will also provide attendees with a PDF version of the presentation near the end of the session. You'll be able to find this under the Handouts tab. Thank you so much for joining. And with that, I'll hand it off to Joe for the presentation.
Hello, everyone. It's truly an honor to participate in this conference and to be part of EE Power Day 2024. I'm Joe Voiles, Vice President of Industrial Power Conversion Products at Advanced Energy, and I'm thrilled to take you on the journey through the evolution of power system architectures. This presentation explores the evolution of power architectures shaped by technological advancements. It discusses the transition from early linear power supply solutions to the benefits of switching power conversion, emphasizing its impact on energy conservation. We will showcase how Advanced Energy's power conversion products can integrate into various power architectures, aimed at helping system engineers, researchers, and power architects with some guidance and insights by analyzing historical trends and anticipating future power requirements. The topics in the presentation include the challenges with increasing energy conservation, product innovation behind the advancements of power architectures. We'll also explore the trade-offs among various power architectures like centralized, distributed, hybrid, high power, high voltage, and we'll wrap up by summarizing our products and capabilities. Increasing energy consumption. As we entered the 21st century, the global demand for energy is on an exponential rise, propelled by factors such as population growth, urbanization, the adoption of electric transportation, the expansion of data centers supporting digital economy, indoor farming to feed the world, and the increasing integration of artificial intelligence. This upward trajectory is anticipated to continue well into the foreseeable future. At Advanced Energy, we embrace the opportunity to address these challenges by offering superior, more efficient solutions that optimize the delivery of power systems. Nearly 2 decades ago, we embarked on a journey to enhance power conversion efficiencies for data center. Over this period, we made remarkable strides, increasing our power conversion efficiencies from 80 to 90%, 96%. This significant improvement in efficiencies had dramatically reduced energy waste, resulting in significant cost savings for our customers. These technological advancements in power conversions have not only bent the curve on electrical energy use, but also made it a significant contribution to conserving energy within the power grid. Without these advancements, the strain on the power grid would be immense, potentially leading to significant challenges meeting energy demand. Power architectures driving product innovation. Linear power supplies started to come to market in the mid-20th century, gaining popularity in the 1960s and 70s as a common technology for providing AC to regulated DC power for various electronic devices. Linear power supplies are typically easier to design than switching power supplies. The fundamental operation and components of a linear power supply begin with tapping into the electrical grid, which typically supplies alternating current AC at voltage ranging from 120 to 230 volts at low frequencies between 50 and 60 hertz. This AC input is stepped down by a power transformer to a lower AC voltage, rectified and filtered to a low noise regulated output. The main drawbacks of a linear power supply are its low efficiency, typically between 50 and 60%, in converting low frequency AC input power to DC output power. The increased size and weight of the power supply is amplified by the need for a low frequency, heavy iron core transformer, large heat sinks, and larger filter caps. As illustrated in our example, a 1,000-watt linear power supply operating at 50% efficiency is dissipating half of its power, 1,000 watts, as heat instead of converting it into usable power. Without the development of switching power supplies, the electrical grid would struggle to meet the growing demand for power, putting significant strain on its capacity. Switching power supplies started to gain widespread adoption in the 1970s. As technology improved and the advantages over linear power supplies became more apparent, switching power supplies essentially converts low frequency AC power from the grid into a DC voltage. This DC voltage is then rapidly switched to a much higher frequency, reducing the size of magnetics and filtering components. Finally, the energy is rectified and regulated to produce the desired DC output. Switching power supplies offer several advantages over traditional linear supplies. Their primary benefits lie in high efficiency, typically 80 to 95%, which minimizes energy loss and lowers operating cost. Additionally, switching power supplies are notably smaller and lighter in weight compared to their linear counterparts. This is attributed to the utilization of high frequency switching techniques, which significantly reduces the size of the power supply. As illustrated in our example, a 1,000-watt switching power supply with a 95% efficiency rating only dissipates 5% of its energy, thus channeling 95% of its energy directly to the output. The advancements in materials and the high efficiency switching components have significantly enhanced efficiencies, reducing wasted power. These improvements enable switching power supplies to deliver more power to the output that significantly enhances the capability of the electrical power grid. This technology not only helps in bending the overall power consumption curve, but also optimizes energy use more effectively. These are some of the ongoing engineering initiatives at Advanced Energy aimed at continuous advancements to improve power conversion efficiency, increase power density, and that enable higher reliability for our designs. Highly effective and efficient topologies and circuits, enhanced magnetics, improved control theory. We're market leaders in microcontroller firmware design with primary and secondary digital control that has significantly decreased the number of components that we use in our design. The use of wide bandgap semiconductors, such as silicon carbide and GaN switching, advanced packaging and thermals, and extensive modeling and simulation. All of these produce, higher efficient designs and better products out to our customers. All of our innovations over the years have positioned Advanced Energy as technology leaders, driving power conversion efficiencies up to 98% on several of our new platforms that will soon spin off to new products for the market that will continue to lower the power consumption curve. How do we do this? We have continued to improve efficiencies while increasing switching frequencies, resulting in significant reductions in size and weight of our power conversion products. Several of our newer products can provide over 100 amps of low voltage power conversion that is about the size of your thumb. In the ever-evolving technology sector, there is a relentless drive to reduce form factors while enhancing packaging capabilities, often leaving minimal space for power conversion. As demonstrated on the chart, we have made significant advancements in elevating power densities, fueled by our unwavering commitment to innovation. Advanced Energy remains steadfast as a market leader in power densities, facilitating substantial size reduction for many of our products compared to the current product market offerings. A major industry challenge revolves around delivering solutions with unity power factor. In an ideal scenario with a resistive load, voltage and current are in phase, resulting in a power factor of 1. However, in practical settings with inductive and capacitive loads, power factors often dip well below 1, leading to phase shift between voltage and current, consequently wasting a significant amount of energy. A simple analogy to visualize the impact of poor power factor is comparing it to a glass of beer with excessive foam. The power provided by the utility company represents the full glass of beer, while the unusable power, or the usable power in applications, equates to the actual beer in the glass, and the foam on top symbolizes the wasted energy. And it's the wasted energy you pay for, but typically gets dissipated as heat, rendering it unusable within the system. As a company, we have dedicated decades of refining power factor correction, seamlessly integrating this technology into our products. Our commitment to energy conservation allows us to enhance overall efficiencies, reduce costs to our customers, bolster power grid capacity, and minimize environmental impacts by mitigating wasted energy. Centralized power architectures commonly feature single-stage AC-DC power conversion with a DC output distributed to the load via cabling or wiring. This straightforward architecture has been an effortless way of powering analog devices and systems for many years. Here are a few examples of centralized architecture. The first one, as depicted, features a separate single-stage AC-DC converter for each output. While effective, this approach tends to incur higher cost and increased size due to the need for individual power supplies for each output. In the second example of centralized architecture, we showcase our multi-output configurable power supply, which is scalable in output power from 400 to 24 kilowatts. Customers can select a chassis according to their power requirements and choose off-the-shelf power modules for each output. This approach bridges the divide between custom and standard solutions, simplifying the process for our customers to assemble a cost-effective, multi-output centralized power solution that offers higher efficiencies, power densities, with the capability to power a wide application with ease. This is a prime example of a centralized architecture, showcasing our configurable power supply equipped with 4 separate outputs, integrated into a system. Each module is wired to individual loads, effectively powering the different process steps required for a 3D printer. This serves as just one example of centralized power solution for our configurable products, are highly versatile and capable of meeting the diverse power needs of industrial and medical applications ranging from 400 to 24 kilowatts that require multiple outputs, all conveniently housed in a single chassis. Visit our website to explore our extensive array of advanced energy power conversion products, seamlessly adaptable for centralized power applications. These products are categorized in low power, mid power, and configurable, and are suitable for a diverse range of applications for centralized architectures. Distributed power architectures commonly feature a 2-stage design approach, beginning with an AC to DC front end, followed by a DC to DC converter close to the load. Here are several examples of distributed architectures. Our first example utilizes a single AC to DC front end power supply to set up a 48-volt DC bus. The secondary stages employ fully isolated DC-DC converters to step down to the lower voltages. While this architecture is still common in telecom and networking applications, this approach has several drawbacks: added cost for the fully isolated converters and the substantial printed circuit board space that they occupy. The most common distributed architecture used today often incorporates AC to DC front-end power supplies, setting up a 12-volt DC bus. This 12-volt bus powers non-isolated DC to DC converters known as point-of-load converters. These point-of-load converters convert the 12-volt DC input down to the necessary lower voltages to power the semiconductors on the board. Today, semiconductor devices require many different output voltages, from 5 volts all the way down to 0.8 volts DC. It's important that these point-of-load converters are located very close to these devices to meet very tight voltage regulation requirements and fast dynamic load response needed for these devices to operate properly. These downstream point-of-load converters can be a mix of discrete solutions, off-the-shelf, non-isolated point-of-load converters. For the lower current requirements, designers typically use semiconductor ICs with some external components to design their own point-of-load converter. But for higher current applications, designers typically look for off-the-shelf point-of-load converter modules to help them address some of their printed circuit board thermal challenges at currents greater than 50 amps. Another common distributed architecture used in telecom and computing applications feature a well-established AC to DC 48-volt DC front end, followed by an intermediate bus converter, which can be either isolated or non-isolated, to step down the 48-volt DC to 12 volts. This 12-volt DC bus is then distributed to the inputs of non-isolated point-of-load converters to further convert to the lower voltages required to power the various semiconductor devices on the board. This is a good example of a widely used distributed architecture, utilizing an AC to DC front-end power supply to establish a 12-volt bus, which gets routed through the printed circuit board to the individual point-of-load converters positioned very close to the semiconductor devices. These converters effectively deliver the various lower voltage outputs to effectively power each of the semiconductors on the board. Explore our website to discover an extensive array of advanced energy standard products tailored to support distributed architectures. Our offering range from a full lineup of AC to DC front ends with a wide assortment of DC to DC isolated and non-isolated converters. These versatile products are suited for a diverse range of applications and distributed architectures. Hybrid power architectures typically combine multiple power sources, including both buck and boost converters, to generate both low and high voltage outputs. Here's an example of a hybrid power architecture, which utilizes our configurable power supply featuring 4 outputs. The 4th output supplies a 24-volt input to one of our standard boost converters, which boosts a 24-volt input to a 30 kilovolt DC output. This highlights the seamless integration of using our standard off-the-shelf power solutions to quickly generate both low and high voltage outputs needed in many industrial and medical applications. Utilizing various conversion stages, as seen in this example, such as an AC to DC 48-volt front end, an isolated 48-volt DC to DC converters, and an intermediate bus converter to establish a 12-volt bus for non-isolated point-of-load converters, demonstrates the adaptability and the versatility of these types of products to create many different architectures to power a wide range of applications. This medical application effectively demonstrates the versatility of our comprehensive range of standard products, meeting a full spectrum of output voltages required to power this complex medical imaging machine from low to high voltage. Please visit our website to discover an extensive array of standard products to support hybrid architectures that can generate both low and high voltage outputs. These product offerings range from a full lineup of AC-DC converters and a wide assortment of DC to DC buck and boost converters up to 60 kilovolts. These versatile products are suitable for a diverse range of applications that can be integrated into many different hybrid architectures. High power, high voltage architectures offers a dependable, scalable, and cost-effective solution for delivering substantial amounts of power across a myriad of applications. One of the challenges in high power systems is selecting the optimal output voltage to minimize power loss. Increasing output voltage reduces current, lowering power losses, enabling the use of less copper for the same power transmission capabilities. As illustrated in the table to the right, with an output power of 3 kilowatts and an output voltage of 12 volts, the resulting output current would be 250 amps. This would require a substantial amount of copper, leading to higher losses. Conversely, if the output voltage goes up to 400 volts, the output current drops to 8 amps, significantly reducing the required copper and minimizing loss. Choosing higher output voltages allows for a significant reduction in current and losses while maintaining the same power transmission capability. Here are a few examples of high power, high voltage architecture we pioneered and developed decades ago. These innovations paved the way for standard high power, high voltage modules that are sized to standard board mounted power DC to DC brick formats. These designs include AC input to 400 volt DC output modules with power factor corrections that establish a 400 volt DC bus. Additionally, we designed a series of high voltage DC-DC converters that can convert 400 volt DC to lower DC output voltage ranging anywhere from 48 to 3.3 volts. These products enable the creation of higher power systems that can be seamlessly integrated onto a printed circuit board due to the higher voltages and lower currents. As a result, these higher voltage platforms evolve into high density, low profile designs capable of powering a wide array of applications in a small package. Here's a prime example of highly efficient three-phase power system that is 96% efficient with high power factor, delivering 30 kilowatts of power in a 2U power shelf that can easily be scalable to over 250 kilowatts, making it ideal to power a wide array of high power industrial applications. This application showcases the seamless integration of our PFC and high voltage DC-DC modules onto a printed circuit board, resulting in a high power, low profile design. It also addresses the demanding needs for smaller power solutions that are highly efficient with high power density packaging for small constrained applications. This high power, high voltage architecture used in indoor farming exemplifies our advanced high power, high voltage architecture. It features a remote power system located outside the grow area that delivers up to 400 volt DC to LED lights inside the grow room. This architecture eliminates the need for LED drivers on top of the lights inside the grow room, minimizing heat generation and reducing the dependency on air conditioning. By combining high voltage architecture and efficient LED lighting with the reduction of air conditioning inside the grow room, this architecture significantly bends the power consumption curve, saving a tremendous amount of energy, making an ideal and sustainable solution for indoor farming operations. Visit our website to discover an extensive array of standard products tailored to support higher power, higher voltage architectures. Our AC/DC product offering ranges from 4 kilowatts to 24 kilowatt building blocks up to 1,000 volts DC outputs. We also have a wide assortment of PFC and DC to DC high voltage modules. These versatile products are suitable for a diverse range of applications requiring higher power and higher voltage. In summary, at Advanced Energy, our mission is clear. We tackle the world's energy consumption challenges head on, delivering an extensive amount of advanced engineering teams worldwide. We innovate high performance products and systems. These innovative solutions not only greatly improve power density and efficiency, but also optimize power factor. Aligned with advanced architectures, our innovations empower our customers, enabling them to overcome their most critical challenges. Please visit our website to explore our full range of products and capabilities. We have dedicated engineering teams to adapt or modify our standard products to meet specific requirements. We also have the capabilities of integrating our products into custom enclosures to meet specific mechanical requirements. Don't hesitate to reach out and let us engineer a solution tailored precisely for your needs. It's been an absolute pleasure exploring the evolution of power system architectures with you. We're grateful for the opportunity to participate in this conference and eagerly anticipate the comments and questions later. Thank you again for your time, and I'm excited about the prospect of engaging with you in the near future.
Joe, it's been our pleasure to have you. Thank you for that great presentation. We've had a lot of good questions come in from the audience already. So if you are ready for those, I will read our first one.
That sounds great.
And that is, what are some of the higher switching frequencies currently employed in your designs?
We're always looking at this, but currently, some of our DC to DC converters, we've driven up our switching frequencies to a megahertz, and it's given us the ability to get the size of these converters down to about, a little bit larger than a penny.
Okay, great. Throughout your presentation, you mentioned efficiency. Can you elaborate on why that's so important and how it benefits the end user?
Yeah, efficiency is really one of our leading drivers when we're developing new product. The higher the efficiency, the lower the energy cost to our customers to run their equipment. So when you look at these big high power systems, even a few watts of savings can add up in a big way to really lower the energy cost that you pay for every month.
Okay, great. Now, do you exclusively offer power switching supplies, or do you also have linear power supplies? And if so, could you talk about that a little bit?
Yeah. Over 98% of our products are high efficient switching power supplies, but we do offer a select product portfolio of linear power supplies, and they're really tailored for lower power, lower noise applications.
Okay, great. And what are some of the applications that require high voltage DC outputs?
Yeah, that's a great question. I think we're seeing more and more high power applications, and we kind of showcase in the presentation indoor farming, and really by going to high power and higher voltage, you can really get to common wiring that's used throughout the installation. So, clearly indoor farming is a big one. We can also take that architecture into, large commercial LED lighting applications that power big box stores, et cetera. But also, from a RF standpoint, there's a lot of high power RF applications. Obviously, with all the electrification going on, high power, higher voltage for EV charging. We look at these real high power medical imaging devices and also supercomputers.
Okay. And how do you decide which topology to follow for a switching power supply?
That's a really good question. I mean, we're always wrestling with the trade-offs from a standpoint of cost, efficiency, density, but we're looking at those topologies and really look at those trade-offs and pick the right topology for the application.
Okay, great. And what are some of the applications that require, oh, I'm sorry. Let me get a new question. What are the potential consequences of insufficient voltage regulation when powering low voltage semiconductors?
Yeah, we've all seen over the years the semiconductor devices needing a lot of different output voltages. And these output voltages, are really can range anywhere on the lower side, 3.3 down to like 0.8 volts. So when you really have the lower voltages, it's very critical that the power source, it has a very precise voltage regulations. And typically, we're looking at about 50 millivolts. And that's why we locate them very close to the semiconductors. because they often need some very fast transient response. And without both the precise voltage regulation and very good transient response, we need to deliver that so that the semiconductor devices can operate effectively.
Okay, great. Thank you for that. So it looks like we've covered our audience questions. If more come in, we can go back to those. But I'm wondering if at this point there's anything you'd like to mention or capitalize on that you hope our attendees will take with them today.
Yeah, I would just say, I mean, at Advanced Energy, I mean, we're committed to deliver high efficient, high reliable systems. You know, we're very focused on that. We've got a tremendous amount of advanced engineering efforts going on to continue to bend that power curve that we talked about in the presentation.
Okay, great. Well, thank you once again, Joe, for that presentation. Before we wrap up, I would like to announce our giveaway winners for this session. Two winners will receive an event t-shirt and wireless charger, courtesy of Mauser Electronics. Congratulations, Sudeep Doda and Tommy Ray. We'll be in touch next week to ensure we have the information we need to get you your prizes. Thank you for attending EE Power Day 2024. In a moment, you'll be redirected to Advanced Energy's exhibition booth. Take a look around and also check out today's other live sessions, keynotes, and published content.